Hey there, science enthusiasts, ready to dive into the mysteries of shadow dimensions? Today, we'll explore how the principles of geometric optics intersect with the fascinating concept of shadow dimensions. So, let's start with the basics. Geometric optics is all about how light travels in straight lines and interacts with objects. It's this simple idea that helps us understand how shadows are formed. Essentially, shadows are just areas where light is blocked by opaque objects, creating regions of absence. Now here's where it gets intriguing. Imagine shadows as projections into higher dimensional spaces. In geometric optics, shadows are the 2D projections of 3D objects onto surfaces like walls or the ground. But what if a higher dimensional object, say from a fourth or fifth dimension, casts a 3D shadow into our observable space? Think of it like this: just as a 3D object casts a 2D shadow, a higher dimensional object could cast a 3D shadow. Let's talk about light rays in higher dimensions. Geometric optics tells us that light travels in straight lines following the shortest path, known as Fermat's principle. But what if light rays interacted with objects in our 3D space from a higher dimensional source? The resulting shadows might reveal properties we can't see with traditional geometric optics. It's a mind-bending thought, but it opens up new and exciting possibilities. Here's another twist: light paths in curved spaces. In non-Euclidean geometries, light doesn't always travel straight. The shortest path, or geodesic, might be curved. So if light behaves differently in these spaces, the shadows it casts would also vary. Imagine a curved, higher dimensional space where the projection of an object into our 3D space results in distorted or unexpected shadows. This could provide a tangible link between non-Euclidean geometries and shadow dimensions. Shadows as dimensional probes? Absolutely. Modern physics, like general relativity, uses non-Euclidean geometries to describe the curvature of space-time. My hypothesis suggests that shadows in curved spaces might correspond to projections from higher dimensions. Just as a 2D shadow simplifies a 3D object, a 3D shadow in a non-Euclidean space might simplify a 4D or higher dimensional object. This bridges geometric optics and non-Euclidean geometries, solidifying the scientific foundation of our speculative framework. And now, the connections to quantum optics. In quantum optics, light has wave-particle duality, behaving as both a wave and a particle. This duality could inspire connections to shadow dimensions. The wave function in quantum mechanics can exist in a superposition of states, which might be similar to shadows existing in multiple dimensions simultaneously. Lastly, let's talk entanglement. Quantum entanglement means particles are correlated in a way that the state of one instantly affects the state of another. Could shadows be interconnected across dimensions? If light sources in higher dimensions are entangled, their shadows in our 3D space might exhibit correlations that defy classical explanations. This speculative idea aligns beautifully with the framework of shadow dimensions as projections from higher realities. So there you have it. The intersection of geometric optics with shadow dimensions opens up an entirely new realm of possibilities. Keep questioning, keep exploring, and who knows what shadowy secrets we might uncover next. Thanks for watching, and don't forget to like, subscribe, and share.